Morning. How's everything going today? Good?
That's good.
You guys excited for football? Any of you guys watch football? Yeah.
First game this week.
Yeah.
This is your first year at Virginia Tech? Your second?
Just starting my second. This will be a third semester in total.
So your last fall.
Yeah.
It's a fun energy.
Yeah. Yeah, it's cool. I like the fall. I like Halloween. That's like my favorite time of year. Okay, let's see here. Why does it think I'm over there? Okay. Shelfin, yes. We gotta talk later. Yeah. About, did you see the GTA thing? Yeah. Okay. It's kind of, I'll tell you about it later. It's good for us though. Lavanya, if you can hear me, just want to make sure that you're able to see the board now, or at least the slides projected. Last time you had a comment about not being able to see what I'm pointing at. So hopefully the new camera position is working for you. Let me know if it isn't. Great. Okay, it's 9:30. Let's go ahead and get started. So it's good to see you all survive the first week and you're still here. That's great. That means that you're going to learn a lot this semester on electromagnetic fields and waves, right? So my favorite thing is waves, and hopefully you guys will enjoy them too. So let's just recap what we did last time. We're looking here at a wave. This is a particular type of wave. This is an electromagnetic wave that exists inside of a rectangular waveguide, which we will study. That mode, that field configuration has a special name. It's called the TE10 waveguide mode. And what we're looking at is the magnetic field of such a mode. So don't worry how that mode is defined. Just know that it does have a physical origin. But this is what it looks like. And the main thing for us to look at is the green vector field, which is the electric field. And then we have the blue vector field, which is the magnetic field. And what we're interested in is the magnetic field of this mode. So what we notice right away is we have some kind of wave, right? Imagine you're in a pool, and you know how they have those little flaps at the end of the pool where the water can go into the filter and clean the water. Well, if you wanted to move that flap, you'd either have to go up and physically move it with your hand, or you can use the medium to move it, to send energy through the medium. And the medium I'm talking about is the surface of the water. So if I sit on the other end of the pool, the opposite end, I take a beach ball and I push it down into the water. Push it down into the water, then I will generate a wave, which is similar to this green wave. And the energy that I impart into the medium is going to travel in the form of a wave all the way through the pool to the end where that flap is, and it'll push the flap. So I can cause sort of action at a distance, if you will, although it's technically not such. But what we're doing is, disturbing the medium with energy in the form of a wave. So that's what we're looking at here. this wave is traveling down the waveguide, and there's a particular relationship between E and H, which we'll study later in the semester. But the main thing I want you to get from this particular slide is that waves are dynamic. The vector fields are dynamic, right? They have temporal dependence. Each of these vectors in here, you can look at one vector, right? It's E, or say H, as a function of X, Y, Z, and T, meaning that if I pick an X, Y, and Z, say this one here, then as a function of time, what is that vector doing at that position in space? It's oscillating, right? In this case, it has a very particular type of oscillation, which is pertinent to our studies, which is called time harmonic oscillation. It's sinusoidal, cosinusoidal. So what's happening here is each of these vectors have a very particular type of temporal dependence. They sinusoidally oscillate up and down, exactly like people do in a baseball stadium when they do the wave. They stand up, they sit down, right? Sinusoidally. Maybe not perfectly sinusoidal because there's some delay between when the wave comes back. But there could be arbitrary temporal dependence, right? We have to remember that. These vector fields with the script H are ones that depend on time, could have an arbitrary temporal dependence. It could be a square wave, could be sawtooth, could be anything. But here we focus on sinusoidal oscillations because what we know from Fourier theories is that you can represent any temporal wave function or any temporal signal in terms of a superposition of sinusoids. So that's why sinusoids are of particular interest. Okay, and then we looked at, well, what does this magnetic field look like? And what I wanted to draw your attention to is these vectors, these blue vectors seem to be rotating, right? They seem to be, they're different than the electric field vectors, right? The electric field vectors, the green ones, they just go up and down sinusoidally, but the blue ones are rotating. What is the difference between the green vectors and the blue vectors? Well, the green vectors have a single component. They point only in the vertical direction. Y, for example. This magnetic field has two components, X and Z. And by having two components and enforcing a particular phase relationship between the two components, I can get the vector field to the superposition, the actual H, which is the summation of these two components to rotate. And I kind of depicted that here in this animation. So we do have HX and HY, or it should be HZ rather. And those two components are oscillating sinusoidally on their own, but they're 90 degrees out of phase. So what happens in that case, we'll see that later in the semester as well, you get what's called circular polarization, or in this case, we just want to observe the vector field can rotate in a circle. That's what's happening here. So you need two components and you need them to be out of phase so that when you add them up, exactly like this, the net effect is that the actual H field is rotating. Okay, great. So the main takeaway here is this vector field is dynamic and has temporal dependence, right? Okay, so how are we going to solve for, we have these vector fields as a function of X, Y, Z, and T, and we need to solve Maxwell's equations for this case in general. So how are we going to do that? Well, if we state, or if we assume, if we explicitly define the temporal dependence to be what we want it to be, say cosinusoidal, what we know it to be, then we'll recast Maxwell's equations into a form which does not depend on time, which is much easier to solve. Inherently, what we're doing, you can think of it as factoring out the temporal dependence, because we know the temporal dependence of every vector is the same, cosine, right? Of course, it has some phase relationship. This vector here is at a different phase than that one, right? It's longer, it's pointing at a different direction in a circular cycle, and this one is at a different phase. I can describe each of those vectors in the family of set that starts out pointing down, then it rotates to the right, then it rotates back up. Each of these, if you take one of these and you define a set, then you can reference each of those vectors in the set with the quantity called its phase, right? Yeah, so one of them I could call phase 0. This one I can call phase pi/2 because it's pointing, 90 degrees per cycle of its rotation. So there is a phase relationship between these vectors, and if I factor out the temporal dependence, if I pause time, if you will, then I'll get a snapshot like this. And all the phase relationship is there. All I have to do is flip the time switch back on and all these things start oscillating, temporally again, and you get the full dynamic effects. So we want to say they're oscillating cosinusoidal, but if I plug that into Maxwell's equations, what do I observe? I observe that I end up still with the Maxwell equation, a differential equation, which is temporal dependent. I cannot cancel sine with cosine because I only temporally differentiate one side. The spatial derivative comes out on the left. So what can I do to get rid of time dependence? I can, instead of calling it cosine, I can say e to the j omega t plus phi. The price I pay there is now I'm working with complex numbers. As soon as I say e to the j, Now I'm introducing complex numbers. And instead of doing real arithmetic, I have to do complex arithmetic. I have to solve differential equations in the complex domain, and I have to do integrations and all of that in the complex domain. But fortunately, we engineers have grown to appreciate the complex number domain. So we'll make use of it here. We'll factor this out. E to the j of phi, the phase dependence goes into the vector field here. Now we're using straight e's. They're not script, which means that they are functions of space only. And the good thing about the exponential function is when I differentiate it temporally, I get the same function back. Therefore, I can cancel them on both sides. And what I end up with is a differential equation in the complex domain now, price I paid, but I've removed the time dependence, right? So here I have the curl of E as a function of x, y, and z is equal to j omega b as a function of x, y, and z. I am missing a minus sign here. That is so bad. Okay, we need to put that in there. Maxwell equation. Of course, on Maxwell equation, I got a sign wrong. So yes, it's curl of E is minus j omega, right? It's here. We have minus partial b partial d. This is correct, but that minus sign got dropped somewhere. It should be here. Okay, let me write it on the slide. Okay, so here, when we differentiated curl of B minus j, there's a minus sign here. Should be here too, all right? That's a fatal mistake, that's critical. So anyway, good. So now these vector fields are complex valued. So I can solve for this snapshot of the vector field in time, and then I can add time back later. And that's where we ended off. Oh no, we got to here, right? So let me clear these markings. Okay, so how do we add time back? Well, we have two domains, right? This is the actual domain. This is over here, time-dependent Maxwell's equations. This is something you can go out and measure in your lab, right? You have to include the temporal dependence when you do measurements in the lab. So this is what models actual reality, the real valued function. You can solve these directly as a function of x, y, z, and t. If you can do so, and you solve it directly, then you get the actual electric field, right? You can measure. Over here, we have time harmonic Maxwell equations, which is the ones we just derived on the previous slide. And here we're going to solve in the complex domain with complex valued functions for the spatial dependence of the fields, which is much easier to solve. In doing so, we're going to end up getting this quantity, the electric field as a function of x, y, and z. And to get back to the measurable quantity, we need to use this operation. The real part of E of x, y, and z, our solution in the complex domain, we multiply by e to the j omega t, and we take the real part. So typically, when you solve problems in electromagnetic theory, you can stop here, right? Because this operation is sort of a step you can take further. It's implied, right? When you publish papers and so forth, you can publish this result, which is most commonly done. Unless you're working with some kind of different time dependence, right? In your paper, you need to specify that I'm using e to the j omega t time dependence and so forth, but it's typically assumed. Good, great. Any questions? That's where we ended up. So let's move forward. Now we're going to study constitutive relations and continuity law. We've seen Maxwell's equations. You guys have seen them in the course previous, or as a prerequisite to this course. So along with Maxwell's equations, we have to introduce the notion of materials, right? If you look at Maxwell's equations, the way they're written up here, divergence of D is rho, curl of E is minus j omega B, curl of H is J plus j omega D, and then we have divergence of B is equal to 0. There's no mention in those equations there, the effects of materials, right? Where do I see in these equations material parameters? They're not there, right? So what we have to do is introduce what are called the constitutive relations. They are these three relations here. We have a parameter epsilon that we're going to introduce. So any material, media, will now have three parameters to describe it. It has an electric response, it has a magnetic response, and it has loss. We convert energy into heat. So these three parameters, epsilon, mu, and sigma, we introduced through what's called the constitutive relations. We have dB and J is equal to, so D is equal to epsilon E. So we relate the electric flux density to the electric field intensity. B, same thing, of density into an intensity, or the other way around rather. And then here we have J is equal to sigma E. This is nothing but Ohm's law, right? So we haven't defined what these parameters are, right? I just introduced them. We will in the next lecture. We'll really understand exactly the origin of epsilon, mu, and sigma, how they relate to the materials, right? How do they relate to the atomic structure of different media? And how can we How are these derived, right? What do they mean? So we'll get to that. But there's one more law we need to introduce, charge continuity law here. And this is the divergence of J is equal to minus partial rho partial T. So remember when we had this divergence intuition, what I want to do is point here. Remember we said that if a flux line enters and leaves a volume, so this is kind of a qualitative picture, if it enters and leaves the volume, then it gives a null contribution to the net flux in that volume, right? That's kind of obvious. If it exits the volume, then it gives a positive contribution to the divergence. And if it enters the volume but doesn't leave, then it gives a negative contribution because the outward normal is in the opposite direction of the flux entering. And in this case, the outward normal is in the same direction. So when you do that surface integral over that face, you get a positive contribution. Okay, so what does this mean? Now, we understand what the divergence is, right? So the divergence of J means if I have a positive value for divergence of J, J means the current density, right? So if I have a positive value for divergence of J, then we know by this case that there's flux exiting that volume, right? That means there's current leaving that volume, which means that whatever charge was stored in that volume is flowing out, right? The current is leaving, current is the flow of charge, and we know that whatever charge is in that volume must be depleting because it's flowing out of the volume, right? And that's exactly what this law says. If I have positive divergence, if there is current flowing out of that volume, net flux of J leaving the volume, then the charge inside must be depleting. It's conserved, right? There's no way charge can either be created nor destroyed. Whatever was in there is leaving if there is current leaving the volume. Yeah? Okay. Any questions?
Does that mean that a point charge is continuous?
A point charge is continuous. Okay, so this law is a macroscopic law, and here we're kind of treating charges as point objects, point particles. I don't know if you want to think of it as like a wave function that's smeared out. There's probably a way to do that, but it's going to be at a level which is higher than what we're trying to understand here, right? Quantum mechanics, maybe.
You're saying current is flowing out, charge is flowing.
Okay, very good. I'm glad you're paying attention. It is the charge that's flowing out, and charge flowing constitutes a current. Okay, great. Any questions? Yes. Yes, there was. I put it in here. Here you go.
Appreciate it. Thank
Yeah, no problem. Okay, great. So now we're going to get into boundary conditions. To prelude boundary conditions, I put this slide together, which is solving ordinary differential equations, right? Whenever we solve an ordinary differential equation, why are we studying this? Because Maxwell's equations is also differential equations, right? And we have to study, or we have to solve Maxwell's equations, meaning we solve partial differential equations. But here we have a first order differential equation, y prime plus 8y equal to 0. And then we have this other condition here called a boundary condition, right? And we'll see why we need that. This is for sure a review for you guys. But so since we have constant coefficients and we must differentiate the function for this differential equation, y prime, we have to differentiate it. We'll try a function y equal to e to the j, e to the rx, right? This is our trial function. So here we have some trial function. We can differentiate that. So here's y, which is our trial function. We differentiate it, r e to the rx. Then we plug it back into this differential equation. So we have r e to the rx plus 8e to the rx is equal to 0. Why do we choose this exponential trial function? Because we can cancel it, right? We can get rid of it here. So this and this cancel, or we can divide both sides by it, but we have 0 on the right-hand side. So we end up with r plus 8. And now we know what r is in our trial solution. So y is then c1 plus, or c1 e to the minus 8x. But we have this coefficient out front, right? Because any coefficient here will still satisfy the differential equation. So what we have to do is use what's called the initial condition here, or if it's a temporal differential equation, in this case, it's a spatial differential equation. So it's a boundary condition. And we use that boundary condition to find what this coefficient has to be. So here we have plotted the direction field for that differential equation, which is a plot of x versus y. We have dy by dx equal to negative 8y. And what we've plotted that here, right? So there are multiple different solutions that we could pick. The solution to the differential equation must follow the slope field, right? The direction field. This direction field indicates the paths. These are the derivatives at all points in space, some representative points. The solution to the differential equation means what function gives me that slope everywhere. And that could be any of the functions that follow this particular slope field, the direction field. So there's a particular solution that's associated with this boundary condition, and that is -2, right? -2 8 to the x, which is this purple curve. Okay, super basic review, I guess, but we need boundary conditions to solve the differential equation to make it a unique solution. So let's look at the electromagnetic boundary conditions. We have two cases here. We're going to solve for, so what does it mean, the boundary condition? I have two media, right? I have one here, medium 2, which has epsilon 2, mu 2, and sigma 2. And then I have medium 1, which has a different set of constitutive parameters. So this is the interface between two different media. And I want to find what is the relationship between the tangential electric field components on the two sides of the interfaces. So there's some relationship between the tangential components and the normal components, right? We're going to use these two constructions to solve for exactly what that relationship is. I cannot stress more the importance of understanding the boundary conditions, right? Because that's how you solve problems in electromagnetic theory. It'll always come down to applying boundary conditions, and you need to understand these. So let's derive what the relationship is, right? If I want to know what the relationship between the tangential components of the, say, electric field on two sides of this interface, I'll use Faraday's law in integral form. E dot dl is equal to negative j omega integration of p dot ds. And you'll see why we're doing that. And we're going to use this construction here. So we have, this is our path. There's one leg that way, that way, that way, then that way. All right. And they go this way. Okay. So we're going, why do we pick this construction? Because I have one tangential component here in medium 2 or medium 1, and I have the other tangential component here in medium 2. Yes, medium 2. The components on the sides, we're going to eliminate those by taking a limit. The limit as delta y, which is the vertical distance of this box, goes to 0. So then we'll get exactly the relationship between the tangential components, just infinitesimally on each side of that boundary. All right, so let's do it. We have this integral of E dot dl. We're going to break that into 4 paths. So we have path 1. Path 1 is minus delta x over 2 to delta x over 2. Here's delta x of ex1. It's in medium 1 times dx, right? Because our dl here for path 1 is x hat dx, right? So let me clear this because it's getting kind of messy over here. All right. So yeah, that's our x hat for path 1, right? The x hat's in the same direction. So then we have plus negative delta y over 2 to plus delta y over 2. That's from here to here, or from here to here, rather. And let me clear this up. Okay. From there to there, E dotted with dYy. You'll see why I haven't expanded or solved this dot product yet, because it's not going to matter. Then the next path is negative ex2, because on the top half of that rectangular boundary, we have this dl vector here. dl is equal to negative x hat dx, right? And we're in medium 2 there. Then we have the path going from here to here, which is this last term. And then we have the integration of b dotted with ds, which is the integration of over delta x and delta y. All right, everybody understand the construction? Yes?
I don't understand why you use X without Z.
Okay, Z is pointing in and out of the board, right? Z is out of the board or out of the interface. We're integrating this rectangular path, which is in the XY plane. So it's a contour integral. So we're integrating along this path, for example, right? This path is in the x hat direction, right? And it has a differential displacement to dx since it's in the x direction, and it's a vector pointed in the x hat direction, right? And we want to find the tangential components, you know, E dotted with dl. So dl is x hat dx. Then E dotted with that is going to pick up the E and the x component of E in medium 1, right? because the dot product of x hat with x hat, y hat, and z hat just picks out the x hat component of E, right?
Oh, okay, yeah.
Okay, so is it clear? So the z hat is normal to the interface that we're integrating around, right?
Okay.
Yeah?
That makes sense.
Okay. I'm okay with you keep asking if you're not 100%. You got it? Okay, great. Okay, good. All right, so on the right side, we integrate over the surface delta x, delta y, right? Good. It's this surface in here. So let me clean this up again. It is that gray shaded surface, right? Because the right side is a surface integral, the left side is a contour integral around the boundary, which is bounding the surface S.
And ds is the normal surface.
Yes, ds. In that sense, we would use dx, dy, z hat, right? As she had pointed out. But anyway, that side is not going to matter because we have to take the limit as delta y goes to 0. Why are we doing a limiting process? We want to know what the relationship between the tangential components directly on either side of the interface, right? Infinitesimally close. There's some jump. There's a discontinuity in E or discontinuity in H. In this case, we're looking at what is the discontinuity in E because of the material discontinuity, right? E is some value in volts per meter on this side of the interface. Say this is the interface. Infinitesimally on the other side, E is different, right? It's 5 volts per meter, for example. Well, in this case, we're going to see they're the same, but it could be different, right? And we want to know how to understand or derive that what is that discontinuity in the electric field as the wave travels through the interface. Yeah?
Will this work if the medium itself is discontinuous, or are we assuming it's if we suddenly have a jump in the material elsewhere integrating?
Okay, yeah. So what we're assuming here is this is a homogeneous infinite medium half space with these parameters. If it had some other jump in here, then we'd have to account for that with another boundary condition for that jump, right? Okay, so let's do the integration. So here we're assuming that EX1 is constant throughout that. Remember, it's a differential path, right? It's a very small path. So EX1 is constant. It comes out of the integral. Then we just have the integral of dx from negative delta x over 2 to delta x over 2. That just gives us delta x. And since we're taking the limit as delta y goes to 0, this path tends to 0, and that path tends to 0. So we don't have this integral or that one. And this one also goes to 0. So we just have the following relations is equal to 0. What does this mean? We can write this like this, right? EX is equal to n, which is the normal to the surface. Here's the normal. N cross product with E2. That'll give you the tangential components, all right? What does this mean? It says, if I throw this term to the other side, right? Then it says EX in medium 1 side of the interface is equal to EX of medium 2 on that side. What that means is the electric field has no discontinuity. It's continuous, right? That's the first boundary condition you must remember. You guys have to remember these. These are super important. Boundary conditions. Remember, these two media are assumed to be dielectric media. They don't have any conductivity at this point. I guess they do have conductivity because of sigma. Okay. Sigma 1 and sigma 2 are finite, though. They're not perfect conducting. So tangential E is continuous. The tangential component doesn't even see the interface. It looks like an infinite homogeneous medium, right? Notice continuity in E, the tangential component. The normal component does see it, all right? We'll see that. Okay. All right. Depending on if there's free charge on the interface. What about tangential H? Follow the same exact derivation and you find tangential H is also continuous. All right? Tangential E and tangential H are continuous across interfaces, dielectric interfaces, interfaces which do not have perfect conductivity. All right? Tangential components don't see the interface. All right, now to solve for the normal components, we derived relationships for tangential components using this sort of a rectangular path. Here we're going to use what's called the pillbox formulation, and we're going to find the relationship between the normal components. So here we have integration in cylindrical coordinates. We have this cylindrical volume here. There's a normal vector here. It's in the y direction. We have the x direction off to the right, and we have z coming out, and we're going to integrate in cylindrical coordinates. We're still going to take the limit as delta y goes to 0. And we're gonna take, so if we did the surface integral, right? Here's Gauss's law in electric form. We have the surface integral, closed surface of d dotted with ds. I'm gonna integrate over all surfaces of this thing, right? Which means integration of d dotted with ds for this gray cap, d dotted with ds for the lower cap, and d dotted with ds for the side, the cylinder, the hollow cylinder side. And you add all those up. Then I have that's equal to the integral of rho dv. So here, delta y goes to 0. I have the first face, which is 0 to 2 pi and phi. We're going to integrate with respect to phi and z, and delta y over 2 to negative delta y over 2. D dotted with rho hat, rho dz. This is the integration of d dot with ds for the cylindrical coordinates for the side, which is the cylinder around the side. Add to that the integration on the top, right? So the top surface is dy2. Here's medium 2. We're talking about dy2 because we took d dotted with ds. ds in this case, so ds for the upper surface here, for this surface, is y hat. Let's see, we need d rho, and then we need d phi, right? And there should be a rho there because of d phi. Rho d phi, right? Here it is, dy2. So we took the dot product, y hat ds is in the y hat direction with d. We pick out dy only, and it's in medium 2. And then we have rho d phi. And we're integrating from 0 to a because we want to cover this whole surface, and from 0 to 2 pi. All right. And then we have the bottom cap, which is here, right? So negative y, because now the normal vector down here, ds, is equal to negative y hat rho d phi, right? Okay. When we take the limit as delta y goes to 0, this term goes to 0. And this term also goes to 0 because we have finite conductivity, all right? This integral, the volume here is tending to 0, right? This is a volume integral over dv. But if I take the limit as delta y goes to 0, I collapse that cube into 0 volume. So that integral goes to 0. So then we just have dy2 a naught. So a naught, I'm calling the area of this cap, minus dy1 a naught. The a naughts can cancel, and you end up with this form of the boundary condition. Says the normal component of d is continuous. All right? Normal component of d. Is E continuous? The normal component of E. Why not?
I'm just trying to think about how, if we have a flow across, like a vector field across the interface, normal component is only existing on the interface, or is there?
No, there could be tangential components. Remember, tangential E is there and it's continuous. Normal D is there and it's continuous. The normal vector on this side of the interface is the same as that one, right at the interface. Yes?
Are you saying that this holds for sigma 1 and sigma 2 finite, or that it proves that that's true?
No, it holds. When we consider sigma 1 and 2 infinite, or either infinite, which we'll do on the next slide, it did different results, different conclusions. We'll get to that. Yes?
You asked why E is not continuous.
Yes.
Normally because of the permittivity.
Very good. Very, very good. So here, remember we had D is equal to epsilon E. And because D is epsilon E, if D is continuous, then and epsilon is different, then E must be discontinuous, right? Because there's a discontinuity in epsilon. Very nice. So normal epsilon is discontinuous, but normal D is continuous. Tangential E, so the ones you use the most, tangential EH are continuous, right? These aren't used as much, but you need to know them all. At least from what I've studied. Same thing with B, all right? B is continuous. Normal B, normal B. All right, good. So now let's look at the other conditions. We have, here's where we're considering infinite conductivity for sigma 1 or sigma 2, right? So same thing. Now we go to the same derivation. The construction is exactly the same. I have integral of h dot dl, and then I have these two terms on the right. This is Ampère's law in integral form. I take the limit as delta y goes to 0. I have the first integral for this first path. I have the second integral here, which is this path. this integral here, which is that path, this integral here, which is that path. Then I have these two terms on the right. Oh my goodness. This is a D. Make that correction, yeah? This is supposed to be D, not B. Copy and paste error. Okay, good. So minus j omega, and that shouldn't be minus either. Copy and paste error. My goodness. So no minus here, and this should be D. Okay, so last time when we integrated this, that term went to 0 because the surface area went to 0 that we're integrating over, and that's still going to be the case. But here we have this term now, which is the integral of j dotted with ds. Now, because we're assuming that there's infinite conductivity at this interface, then that allows there to be a infinitesimally thin layer of current at the interface, on the exact interface, right? So right here, at the interface, that there can be a surface current flowing. Because what I'm going to do when I take the limit as delta y goes to 0, I collapse ever closer, closer, closer to that line that represents the boundary, but there's still two sides to that box, the medium 1, medium 2, and then now there's this surface current sitting in there, right? Because I can infinitesimally keep closing that box all the way to 0 as delta y goes to 0, but there's still some surface current flowing because of the infinite conductivity means the current can flow at the infinitesimal layer. So this is a super important boundary condition. This one, written like this normally, the tangential H is discontinuous by the amount of surface current density. This reads in the following way. If I have a surface current density at some interface, the tangential H field must be discontinuous by that amount. That's what this equal sign means. Surface current means discontinuity in H. Conversely, if I have a discontinuity in H, then there must be a surface current density present to support that discontinuity. All right? Tangential H is discontinuous due to surface currents.
So I guess in the real world, we have actual atoms. How do we have that infinitely thin?
So this is a macroscopic model, right? And macroscopically, okay, so yeah, I mean, you can't take the limit all the way down to an atom. But we're assuming in a macroscopic model, when we don't consider microscopic effects, that we can get close enough to the boundary that the only thing left is a surface current sandwiched by two tangential H vectors, right? And I can make those tangential H vectors closer and closer and closer and closer around that current until you can do that forever, right? In a limit sense. Okay, let's look at d dotted with ds again, but now we're assuming that we have some conductivity. So what's going to happen is this integral, the only thing different is that integral is not going to go to 0. So we're going to integrate it. And what we get is called a surface charge density, because surface charge can exist at the infinitesimally thin layer sitting right on the boundary. Therefore, the tangential D is now discontinuous by the amount of surface charge. So the way you read this is, if a surface charge is present, then D must be discontinuous. Normal D, and dotted with D, which is the normal component of D. And if I have a discontinuity in D, then I can infer, I know for sure, with confidence, that there is a surface charge density present there. Yeah?
So this is true even if it's not truly infinite conductivity. This is a
Yeah.
condition for copper or something like that.
For sure. Yes, that's a great observation. So what we're going to find later is there's a thing called skin effect and things where charge can exist inside. So that kind of complicates things. But here we're talking about there's a hard boundary between infinite, where we definitely have infinitesimal layers of current and charge, and then finite, where we don't. But in practice, copper is assumed to have this kind of infinite conductivity, and we would use these boundary conditions. Copper supports a surface current, right? And we would use this exact boundary condition. Matter of fact, anything that we would call a conductor, we use this, right? And anything that's a dielectric, we'd use previous ones, so we call it finite conductivity. Good observation. Yes?
In the math, where did you make a change that led to that different result?
Okay, in the math, the only thing that was different is this term appeared. Okay, last time we did Faraday's law, here we're doing Ampere's law. Okay, this one down here, we did the same thing, right? Nothing different in the math, right? We just, okay, so there is a step here where we take the limit, we distribute this limit to this side, right? And we have the limit of this, and you can assume some like delta. It's a book, if you look there. The steps to kind of rigorously show that this becomes a rho S here, right? So I'll defer you to the book, but there is, if you take this limit and you distribute to this integral here, then you can rigorously define what is the meaning of surface charge, right? There's a definition of that. Here I just said this integral leads to surface charge, but there is a step missing for that. Very good. Good question though. I like that. Yes.
I couldn't get why you use the conductivity for your condition in the second terms, I mean the D. It just depends on the charge, whether it's we have a charge or do not have a charge to that the D would be continuous or discontinuous. What's the relationship between that to the conductivity?
If you have infinite conductivity for this medium, say this is a conductor and this is dielectric. If you have infinite conductivity, then any charge you place in that medium is going to flow to the surface, right? And where will it show up? It'll be on the surface only, infinitesimal layer on the surface.
We have two dielectric together, but we have a charge in the boundary, so it works. Both of them would be finite conductivity, but you still have that conclusion.
This is free charge here, right? This is not bound charge, polarization charge, so dielectric, we'll see in the next lecture. If you can somehow place a charge density at the interface of two different dielectric media and have it stay there, then you would probably use this boundary condition as well. But in natural materials, I don't think you can place a charge, somehow impress a charge at the interface between two dielectric and have it stay there at the interface like that. Normally, two dielectrics support only what's called, they don't have free charges. There's no conduction band. So they just have what's called a polarization charge. We'll study next lecture. And that charge does not contribute to this law, the bound charge. Okay, very good. Good question. Yes.
I like to think of it as like an instant ray of light on a material with two different things, and it mixes with diffraction. So that might be, this is like the equivalent of electromagnetic Snell's law.
Yes. Yes. Very good. Yeah, definitely. So according to Snell's law says that the tangential components are continuous, right? Snell's laws are derived from these boundary conditions. You apply these later on when we're doing incidence on interfaces. But in that sense, yes. Here we're assuming that there are fields established already in these two media. And we're finding the relationship between the two based on these parameters. But when you're talking about wave incidence on an interface, we'll study that later. Yeah, they're definitely, these laws come into play and they lead to Snell's law. Great. All right, guys, very nice. So let's get moving here. So here, table, this brings everything together, right? So we haven't introduced this concept of magnetic surface current. This is sort of a fictitious quantity, but it's useful in derivations. If we assume that that's there, then we complete the symmetry of Maxwell's equations, and we can use it as a mathematical tool to solve problems, even though it has no physical origin because we have no magnetic charges, right? So there can be no magnetic current. But what do we define it as? We use this law right here. We say if a discontinuity in E, which does exist, we can model it as a magnetic surface current, right? Okay, so here, finite conductivity media, there are no sources or charges. Sigma 1 and sigma 2 are not infinite. The surface currents are therefore zero, and the charge density, these charges are zero, right? We get everything's continuous. Tangential E and H are continuous, normal D and B are continuous, right? These are the general laws. These are what you should remember. Then here we have medium 1 of infinite conductivity. So one of the media are infinite conductivity, like a conductor, and then free space on the other side, for example. These are special cases of these laws, right? On a medium 1, so I have some metal sphere, for example, and I have free space all around it, metal sphere and free space. That discontinuity, that interface between the metal and free space, tangential E goes to zero. And we'll understand that later because tangential electric field on an equipotential conductor or equipotential surface is zero. Tangential E is zero because what happens is E1 is zero. There can be no tangential electric field, no electric field inside of a perfectly conducting material. We'll see that. There's a surface current density present, but it's only related to magnetic field on the outside, on the free space side of the interface. The normal charge density, the normal electric flux density component terminates on the charges on the metal, and there's no magnetic charges even in conductors. Here we have a medium one of infinite magnetic conductivity, if it had such a thing, then it would be the opposite. B would terminate on the magnetic charges, D would be 0 at the interface, and then tangential H is 0, and then we have this conductivity or this relationship between the magnetic surface current that exists. All right? This table, refer to it when you're solving problems and things.
Magnetic monopoles, or is it saying that it's a magnetic dipole? We have a sphere.
Well, they'd have to be monopoles, right? They're charges that flow that constitute a current. I think if you assume that they're dipoles and they're flowing, how do I define a current? Charges flowing through some spatial screen, if you will, some meter squared surface, and how many flow through in a given amount of time, right? How many coulombs? So if a dipole flows through, then the net contribution of that is 0. So probably wouldn't it had to be monopoles. There are uses for magnetic imposing or assuming magnetic currents and things. We'll see. Okay. All right, let's get to power and energy. We're almost done with the classical electromagnetic theory and ready to move on to some interesting things. So here, what is the electromagnetic power? What is the power associated with an electromagnetic wave? Well, we have this definition, which you've seen before, called Poynting's theorem. S, which is the power density. This has units of watts per meter squared, and it is equal to E cross H. So it's a vector relationship, cross product. I have E, I use my right hand. E in the direction, my fingers in the direction of E, I curl them to the direction of H, my thumb points in the direction of power flow, or the Poynting vector. All right, well, we know we can define, this is in the time domain, there's script letters, S, E, and H all depend on X, Y, Z, and T. I can convert these to expressions involving the time harmonic Maxwell's equations that are dependent only on space, X, Y, and Z, by using these expressions, right? E we know is real part of E into E to the j omega t, and then we can write that as 1/2 of this plus its conjugate. That's what the real part is defined as, right? So I can take S, I can substitute in E and H, I can carry out the cross product operations, and what do I end up with is this expression here, 1/2 of the real part of E cross H conjugate plus the real part of E cross H e to the 2j omega t. Now what I'm going to do is take the time average. I'm going to integrate over one period of the sinusoidal function. We're assuming these are sinusoids now, right? So integrate over one period. This term drops off because we're talking about 2 to the j omega t, 2j omega t, right? So integrating that over one period will give you a null contribution. And what I get here is the time averaged Poynting vector, which is a straight S, and it is 1/2 real part of E cross H conjugate, right? That's how you calculate power density.
So how is assumes to have a time component in units? So what does straight S really mean?
Yeah, this is watts per meter squared in a spatial sense, right? So this is the watts per meter squared. Here, I believe you still have units of watts per meter squared because E and H don't have different units. But it's power, right? If you're talking about energy per unit time, then you'd probably want to make an expression for energy. I think we'll see that here soon. Okay, good. So 1/2 real part E cross H conjugate. Probably seen it before. That's where it comes from. So now let's derive a conservation theorem for power and energy in a medium. So, okay, we're going through all this classic electromagnetic theory. We'll get through this and we'll get to some super exciting things about media waves and all of that, the fun stuff, but we can't do any derivations or understand anything until we understand all of this classical stuff. So let's get through this. We have a volume V bounded by a surface S. The material parameters are epsilon mu sigma inside. There's a normal vector n hat. There's E and H outside and an E and H inside. We have Ji and Mi. The subscript I stands for impressed. A source is impressed when I can just place it into a medium, right? That's called impressing a source into some medium, meaning that it's not from, so there are different kinds of sources, right? Impressed source, the best way I can describe that is I can just take a current density and I can place it right here in this room somehow. Forget how physically that can happen. I just say that there's a source that is comes into existence at this point in space. Impressed it into the medium, all right? So Ji-Mi. So the Maxwell's equations must be satisfied. Curl of E is minus M minus j omega mu H, and curl of H is J plus sigma E plus j omega epsilon E. right? Okay, so we've seen this as J, right? This is J. The curl of H is equal to J plus partial D, whoops. Partial D, partial T, right? But in time harmonic form, this term goes to J omega D, right? This is the new term, J impressed, which is a current that I've added, right? It's another source. Okay, good. So what do we want to do? We're going to take the dot product of Faraday's law, this one, with H conjugate, and the conjugate of this law, the entire law, by E. Why are we doing that? What is the motivation, right? I'm trying to start with Maxwell's equations and come up with an expression that has units of power. So that's the motivation. I want to construct from Maxwell's equations, new expressions that have new insights into the physics by combining them in certain ways, right? If I have two equalities, I can add them together, I can subtract them. As long as I maintain that equality, the new expression that I construct from the two previous are also valid. So H conjugate dotted with this, and then the conjugate of Ampere's law dotted with E, right? So what I'll notice is H conjugate dotted with M and E dotted with J I conjugate, and E dotted with J conjugate. That's power. Sigma E conjugate dotted with E is also power. So I'm starting to get somewhere. Now I have two expressions. I'm going to subtract the two. I want to construct the pointing vector. There's motivation for that operation. So E conjugate dotted with the curl of H minus H conjugate dotted with the curl of E. So I'm just subtracting this expression from that one. And then I have all the other terms, right? Because of this vector identity here, the left-hand side becomes the divergence of H conjugate cross E. So I'm almost to the pointing vector. Some more mathematical operations, and I can write that as minus the divergence of the E cross with H conjugate, which is what I want, right? Then all I'm going to do is multiply by 1/2 throughout, so I can get the 1/2 E crossed with H conjugate. That's my pointing vector. So here it is, the conservation of energy in differential form. It says, we'll dig into what it means in the next slide or two, but here we have the divergence of pointing vector. Back to our divergence intuition. May I have that on the next slide? Yeah, here, look, the divergence intuition. When some flux of some vector field, now we're talking about power flow. The pointing vector is a vector field. If there's power flowing out of the medium, if S dotted with ds is a positive contribution, then there's power leaving the medium. Power is the flow of energy. Then the energy in that medium must be decaying, right? It must be decreasing. Power is flowing out of the volume. Then the energy in that volume must be decreasing because power is the flow of energy. Okay, so we'll get back to that. So here, so if there is power leaving a volume, okay, so the total power, this is an accounting equation. I add up everything and account for everything. If power is leaving the medium, right? And I guess this minus sign would mean that E cross H conjugate is flowing out, divergence. So yeah, if power is entering, the power entering the medium is entering, right? That has to be equal to the power supplied by the source plus the power supplied by the electric source plus the energy decaying in the medium, lost due to dissipation, dissipated in the medium due to heat, plus the energy stored in the medium is what this is. We'll dig into the terms. Don't worry if they're not making much physical sense yet. We'll dig into them.
Can you please explain the significance of this impressed concept?
Yes. So we're saying if there are some sources in the medium, right? We're not giving their physical origin. We're saying if there is some sources in the medium, then I'm going to call those impressed sources. All right. What's that?
Are we assuming MI and JI are coupled somehow, or are they independent of each other?
They're independent, right? They're two different sources. Yeah. Okay. Yes.
Does that mean that the past existence or the past behavior of the interest sources are not really relevant to the current situation? Because we are assuming that they just exist. So we are not taking into account existence.
How they got there, right? Is that what you're saying?
Yeah.
Yeah, that's the thing. So we're trying to remove the physical origin of these sources. is it a wire with its voltage source connected to it? Then I have to describe the voltage source, the wire, the geometry of the wire, right? Is it an aperture where I have some kind of like flashlight kind of shining through a hole in a PEC screen? I want to remove that discussion and just say there are sources of electric and magnetic field, right-hand sides to Maxwell's equations, right? That are existing in the medium. And I'm assuming that they're impressed, meaning I can just place those sources there and let those sources radiate and generate due to Maxwell's equation. I have J. Once I have a J, then I have AH and E and all that, right? I just plug J on the right-hand side of Maxwell's equation. Those sources, I'm just saying there's a J there, right? Forget how they're physically created. Very good.
Basically, we are trying to like eliminate any kind of temporal dependence. Just stating that it's a snapshot of the charge, the source that already existed in the media, and we're not interested with any kind of time.
Yeah, so here we're working with straight H's and E's, right? So this is time harmonic domain. So we're assuming everything very sinusoidally. We factored that out of the problem, and we're solving for the spatial dependence. And also one thing, when we're dealing with time harmonic domain, we are talking about steady state solutions here. All transient effects have happened infinite time ago, all right? So the fields have settled into what they're going to be, and everything now is feeling. So let's say I have a source here, impressed source. I have a J here. I place into the room here. It starts oscillating like this. It's a dipole of this length. What's going to happen? Radiation is going to spring out from this point. We'll study that and we'll solve that mathematically. But that radiation is going to go reflect off the table, reflect off the walls, reflect off of all of you. It's going to fill this whole room, right? Remember, this radiation, whatever frequency it is an electromagnetic wave, so is light. So the same thing when I come into this room when it's dark and I flip the light switch on, it fills the whole room with light, right? But prior to that, there's a transient phenomenon or time period where the light reflects off the tables and it's going everywhere. And there are parts over here that's dark. So when I turn on the light bulb in that corner of the room, it's dark over here until the light gets here. But in steady state, it fills the whole room, right? And if we weren't moving and the medium was static, then there'd be an electric field, which is static in steady state, right? And that electric field, of course, it's oscillating, but if it was oscillating sinusoidally, then I could say, okay, remove time dependence. What does the electric field vectors look like in this room that fill up the whole room, just like the light filled up the whole room as a function of space? And then there's a phase relationship between all those vectors, right? So this source would fill up the whole room. All that reflection and all of that has happened infinite time ago. Everything is now static, steady state. Nothing's moving. I can solve using Maxwell's equations for what that electric field looks like. And then I can add time later if I want, assuming that the sources are sinusoidal, temporal dependence. Okay, good. So let's dig into this and figure it out. All right, so let's define some of these terms. Now this side, okay, so I moved the minus sign to the other side because it's easier to understand. Power leaving the medium. If I have a divergence of S, that means that there was net flux exiting the medium if the left-hand side ends up being positive when I take the divergence of E cross H conjugate. That means power, there's flux lines of H exiting this medium that did not enter the medium. So there's a source of power in that volume. If there is a source of power in that volume, then this equation tells me that that source is the power density due to the increased or impressed magnetic current source must be decreasing because power is flowing out. So whatever is the source of that vector field flux that's exiting the volume must be deplenishing, right? Deplenishing should be decreasing. Then we have also the power due to the electric impressed source is also decreasing because power is flowing out. There could be power dissipated in the medium, right? So I have to account for that. And then there is a decrease in stored electric or magnetic energy in the medium. There could be some capacitance in that medium that stores electric energy, but if power is flowing out, we'll see some special cases of that right now. Okay, so one thing is this is generally a complex number, right? Power flowing out. So that means there's on the left-hand side of the equal sign, we have generally a complex number. So there must be a complex number on the right-hand side in general. So this is generally complex, means there's power stored and power dissipated due to these sources, right? And then this is always real, right? Dissipated power is always a real value. And then this is always reactive. Stored energy is reactive. You can get it back, right? Okay, so let's look at the conservation of energy here. in a little bit more detail. So here it is again. Now let's make it a little more familiar to ourselves. Let's look at a lossless point in source-free space. Source-free means there's no impressed sources, right? So Ji and Mi are 0. These two terms are out. Then I have, it's a lossless point, right? So sigma is 0. And then I just have the divergence of 1/2 E cross H conjugate is equal to the rate of change of the electric stored energy. This, using our divergence intuition here, says that if power is flowing out of the medium of a point, the surrounding volume around a point, then the energy density at that point must be decreasing. Remember, every time you see J omega in time harmonic Maxwell's equations, that's nothing but partial by partial t, right? Because we assumed the temporal dependence e to the j omega t. We differentiate with respect to t, then j omega comes down. So you can kind of mentally replace or think of j omegas as time dependent, time derivatives in time harmonics. Minus time derivative means that this quantity is decreasing in time. The energy density, we'll see why these are energy densities. They decrease in time because power is flowing out, and the flow of power is the flow of energy in time. Good. Okay, let's compare this to this law, which we understood. If current density is flowing out of a point, then the charge density is decreasing at that point. Same thing here. Energy is decreasing if power is flowing out. All right? Here's another familiar example. Okay, so another copy paste error. This is not source free. There's a source here. Okay, so it's a lossless point still, but we have electric current density. Yeah? If the source of power flux, right? The divergence of some quantity compared to this, divergence of D is equal to rho. The way we read this, I take the divergence of some vector field, that operation, taking the divergence of some vector field tells me the points of sources or sinks of that vector field, right? The sources or sinks, according to Maxwell, of the electric flux density are charge density, right? If there is a charge, that's a source of electric flux density D. If I have a charge, a line of D will be created. If I have a minus charge, a line of D will terminate on that point, right? Okay, same thing here. If I have power flowing out, it is supplied by the sources. That power is decreasing. So this is the source and sink of pointing vector, power flux. Make the analogy, yeah? Good, great. Okay, guys, all right. So you can write this in integral form. I just integrate both sides and apply the divergence theorem, which is what I did. Divergence theorem, or in this case, divergence theorem, right? So you can integrate everything, and by integrating these quantities, instead of them being per meter squared, per meter, I can call these watts, right? So supplied complex power in watts. The source, the power supplied by J and M, that power supplied is equal to, it's distributed in these different components, right? The power I supply by the source in the medium either exit the medium, or they get dissipated in the medium, or they lead to stored energy in the medium, right? Like in capacitive inductance. So that it's accounting, right? Great. Okay, let's do an example. So this kind of conservation theorem is kind of hard to really get your mind around it. So that's why I added this example and those other kind of simpler cases. So here we have a section of rectangular waveguide. We'll understand this later, how to analyze this, but it's a rectangular hollow pipe. And you can send, so if I have this source here sitting in free space and it radiates, there's no boundary condition, right, for this. It radiates in all directions. We'll see, okay, so it has some pattern, but essentially you can, it was a point source. It radiates in all directions, right? If I want to funnel that energy to somewhere else more efficiently, if I was trying to communicate with her, for example, and say my voice, it's still a wave, right? It's acoustic wave. If I'm talking to her, then I talk at a certain volume, but I waste energy because it's going everywhere, right? My voice, the energy, the wave is spreading everywhere. If I wanted to spend or direct my energy directly to her, I could get like a wrapping paper tube, right? You have wrapping paper for Christmas, all the paper comes off it, you just have that cardboard tube. I can talk through the tube at her, and my energy will go through the tube, the wave. It won't spread out, right? It'll go directly through the tube to her. So that's a way to guide energy in a waveguide so that it's more efficiently transported from one point to another without losses due to diffraction. Here, it's the same thing. I can send an electromagnetic wave in this rectangular pipe, and because of the boundary conditions that are created by this waveguide, the geometry, the metal, I can more efficiently send energy from point A to point B. We'll study it later, but this is the electric field that exists in there. So here is the conservation theorem. For a section of waveguide of length L, so this distance here is for some section of length L along the z-axis, verify the conservation of energy equation integral form is satisfied for this set of fields. So I'm telling you this is the electric field inside. Okay? Don't worry about how it's derived, but assuming that's the electric field. So let's do it. All right. First thing we're given E, let's find H. Whenever we have E, we solve the problem because Maxwell's equation allows us to find H, right? So we have E, H means the curl, so I use Maxwell's equation, which is the curl of E equal to minus j omega mu H, I can find H. So I need to take the curl of E. Well, here is E, it has a y hat component, and I'm telling you if you take the curl of E, you get this expression here, right? It has a x hat component and a z hat component. And you can use that expansion of the determinant in this regular rectangular coordinate system. Okay, so now that we have H, we can find E cross H conjugate. We can conjugate that and take the cross product with E. And we end up with this expression here. All right, you can go through the mathematics to verify this. Then, now that we have E cross H conjugate, we can start piecing together the theorem. So there are no impressed sources, right? There's just fields. There's no sources. So that means this term goes to 0. There's no conductivity in the medium filling the waveguide, it's free space, so that term goes to 0. And then the first term is, we use the divergence theorem here to rewrite this as the surface integral around this volume. So it was the volume integral of everything filling this medium, right? But using the divergence theorem, I'm going to integrate E cross H conjugate on these surfaces, the bottom surface, the side surface, and then the caps at the ends. All right. Okay, so if we do that, we have 1/2 E cross H conjugate here, dotted with z minus z hat dx dy. Why? Let me ask you why. Why is this the only term for the caps? Okay, let me clear this up. Oh shoot, I think it's getting too messy here. Okay, this term here is the two caps, the end caps at L and minus L. So I integrate from 0 to A, 0 to B, which is the cross section, E cross H conjugate z hat dx dy. And then I have the other term. If you split this into two integrals, you get minus z hat dx dy, and then you get one with z hat dx dy, which is this front cap is z hat dx dy, the back cap at L away is minus z hat dx dy. So I combine them into one integral. Then we have the sides, right? From 0 to B and from 0 to L. So 0 to B here is from here to here and from here to here. So we're talking about this back face here. That at x equals to 0. So here's the x-axis, so x equals to 0. We evaluate E cross H conjugate there. This is 0 because the electric field there is 0 at x equal to 0 by nature of the boundary condition, right? Same thing here at x equal to A. We have also 0. So this term, the integral of the divergence, so this term here has reduced to, okay, so this term is equal to 0. All right, what does that say? All the power that enters this face of the waveguide must exit the back face, because if you take the difference in the power that entered and the difference in the power with the power that exited, you get a result of 0. All right, that makes sense. It's maybe it's a cheesy example, but what happens, it verifies. We use this theorem, all the power that enters this medium must exit. We chose a waveguide because we know the fields. Okay, go through the math if you want to understand that a little more in terms of the mathematics, right?
So this is a real waveguide and we have loss. It would only be on the surface current of the walls.
Yes, very good. So if this had loss, then the difference in the power that entered, E cross H conjugate dotted with Z, minus E cross H conjugate dotted with Z hat, which is the power that exited, would not be 0, because this would not be 0. The difference would be the power that was lost in the walls as it went from 0 to L in Z. Good. Okay, so we didn't calculate the energy, right? So the first, okay, that was, we looked at this term here, and we know that this term is 0 because of no impressed sources. And we know this term is 0. We still have this term, right? So let's verify that that one is 0. Okay, so H, we know what H is. We found H. We can dot it with H conjugate. We get this result. We do the same thing with E. We get this result, right? Now we need to multiply by mu naught, epsilon naught, and 1/4. We need to subtract the two and integrate over the volume and multiply by J2 omega. All right? And if you carry out those mathematics, which I put all the steps here for you, then you end up with a value of 0, which is exactly what we expect. No energy was stored in the medium. It's free space, right? Inside there, so it can't store. Very good. Okay, refer to that later if you want. Okay, so a few more small things that you're going to need as tools to solve your problems in electromagnetic theory coming up this semester is transformation between coordinate systems. All right, this is a slide that you should use as a reference. Whenever I solve a problem in Cartesian coordinates, or if I have a problem that's written in Cartesian coordinates and I want to convert it to a problem that's written in spherical coordinates, I can use these transformation matrices. Have you guys seen these before? You're going to derive them in your homework. So you'll see exactly where they come from. Here I'm going to state them, but part of your homework is going to be to derive these matrices. All right? And you can go from cylindrical to spherical, and then spherical to cylindrical, or you can go from rectangular to cylindrical and cylindrical to rectangular. Or the ones on the top are rectangular to Cartesian. All right? Very useful. Another topic which is super useful is called Eulerian angle transformations. So on Canvas, there's a folder in the files section that's called reading material. You're going to read this paper that leads to these expressions. Very useful. If I have a problem that has two different things, like a reflector and an antenna, a horn antenna, then the fields of the horn antenna are most conveniently described in a coordinate system which is centered about the aperture of the horn antenna, right? So I have some feed to a reflector antenna. I have one coordinate system which is defining how the radiation from that feed is most conveniently described, right? If I had a coordinate system on this reflector, like this, for example, over here, and I had some horn antenna over here, it'd be really hard to describe the radiation due to this horn antenna in terms of this coordinate system. It's displaced and the angles are very different, right? But I can have two coordinate systems in one problem. I have a horn antenna, has its own coordinate system. I have a reflector here, like a parabolic reflector, like a satellite dish, that has its own coordinate system. And I can describe the radiation reflected from it easily in its own coordinate system, and the radiation from the horn antenna easily in its own coordinate system. How can I relate the radiation due to the horn, described in this coordinate system, to its description in this coordinate system? Because this horn is going to illuminate this reflector. So I want to take the description of the fields in this coordinate system and convert them or describe them in this new coordinate system that's on the reflector, so I can find out what the incident fields are on this reflector. All right? For that, I need to convert between two coordinate systems. So I have some vector A, right? This vector A in coordinate system 1, which is unprimed, X, Y, and Z. I have that same vector, right? It points in the same direction in space. It's got the same length, so it's the same A, it's a physical A, but I'm gonna describe it in a coordinate system, right? Remember, the coordinate system is your choice. You pick the coordinate system to solve your problem. The physical vector field A is there, but I can pick my coordinate system to most conveniently choose or solve the problem. So it's your choice. So there's another coordinate system, X prime, Y prime, Z prime, that I have that same vector A in. How do I go from a description in this coordinate system of A to this coordinate system description of A, right? There's a systematic way to convert one description into the other. And it's called Eulerian angle transformations. So I have what is A in the primed coordinate system when I know the components of A in the unprimed coordinate system. I need to derive this matrix called the Eulerian angle matrix, which is called C prime AC, which is it's a matrix A, which takes you from unprimed Cartesian coordinates into primed Cartesian coordinates. And I need to derive this matrix. Its definition is here. If you decompose what this definition is, it's 3 rotation matrices, right? About one axis. here you might have recognized this matrix. This 2 by 2 upper left part of this is a rotation matrix, right? If you write it in 3D like this, it's a rotation matrix about this axis Z. So the first rotation, and it's a cascading of 3 rotations to go from this coordinate system to that. So what does it say? Okay, I start with, there are three angles, gamma, beta, and alpha, right? You start in the unprimed coordinate system, this one, and you rotate about the Z-axis through angle alpha. So here's Z-axis. This axis doesn't change, but the XY do, right? So I start with the Z-axis and I rotate through angle alpha. So I start with Z here, right? This is the Z-axis. I rotate through angle alpha, the X-axis, until it aligns with this thing called the line of nodes. So see these discs? These discs here are the XY planes of the primed and unprimed coordinate system. So here, this disc right here has a normal vector Z, and that is the XY plane of the unprimed coordinate system. This other disc here has a Z prime normal. It's the X prime Y prime plane, right? These two discs are surfaces and they intersect in a line. That line is called the line of nodes here, right? It's a common sort of line in the two coordinate systems. So the first rotation, I rotate about the Z axis through angle alpha till X aligns with the line of nodes, right? Then I rotate about the line of nodes through angle beta until the Z axis aligns with the Z prime axis. Then I rotate about the Z prime axis through angle gamma until the X axis now aligns with the X prime. So what happened? Z went to Z prime and X ends up going to X prime and Y is along for the ride. So now they all align. So those 3 rotations align the coordinate system. That same matrix that was used to align the 2 coordinate systems also describes the components of A and A prime. The same matrix. Okay, great. Read the paper. It's part of your homework.
Is the line of nodes the eigenvectors?
I don't know if I would say that. No, I wouldn't say that. Okay, let's see. This is probably a good place to stop because we're gonna get into a new topic. All right? All right. So good. You guys are all getting your knowledge up in this area. We're almost to sort of some interesting things. Now, you're gonna have a homework on Thursday. It's coming out on Thursday, and it'll be due a week from Thursday. And there's a reading assignment. There's 2 reading assignments in that folder called reading material. Make sure part of your assignment is going to be to read those papers. The best thing you guys can do, if you really want to be the best engineers that you can, I know all of you do, is to read everything, right? You're learning things from the lecture, but go read it in the book. And then once you read books, I mean, it's a win-win scenario. You learn so much information from reading. So I would, if you have time, read the book, right? Part of your assignment is going to be to read the chapter. And I've spent, over the years reading this whole book that we're learning. So it's a good book. Okay, so homework Thursday, that will be coming out. And there's office hour today. If you need me, I'm in my office. And that's it. All right, see you Thursday. Okay.
Can you explain what you mean by motivation in this power?
So I have these 2 equations and I did this operation dot product of Faraday's law by H conjugate. Why did I pick to do that? Why would I all of a sudden think of H conjugate dot with Faraday's law or E dot with the conjugate of Ampere's law? The motivation for choosing this operation is that it results in units of power. E dot with J is units of power. H dot with M is units of power. And then that was the motivation. Sigma E conjugate dot with E is also units of power, right? E conjugate E, remember E is volts per meter. So E conjugate E is like magnitude of E squared, volts squared. And then sigma is like 1 over R. So then you get sort of V squared over R, units of power, right? From circuits.
Okay.
Yeah.
I think it was overthinking it. Thanks.
Yeah, no problem. Yeah, great question. So we know what electric current is. Electric current is the flow of electric charges, right? If there were magnetic charges, which we know there's not discovered yet, if there were, the flow of those would constitute a magnetic current. It's the dual of electric current.
Okay, but
Now-
it's like an imagined
Yes.
component for us to solve.
We'll use it as a tool.
Okay.
Say there was some magnetic current, then we can model the discontinuity E in terms of it. And then we can use that to solve problems. You'll see that later where we can have aperture fields of time varying electric field. We can model as a current density. It's a useful construct,
But it has no physical.
no physical meaning.
Okay, just a mathematical.
Yes.
Okay.
Yes, just a mathematical meaning. And we'll see somehow that helps solve problems.
Okay.
And we can assume that it's there, but in the end, it won't matter that it was really there.
Okay, that makes sense.
Yeah, good.